going to briefly show you an exercise we did with graphing a rational function. Okay, and you're not necessarily going to understand this. In the MBE class, we're doing a few things that are ahead of this, so people have a little head start. But it's like this, okay? So it's a polynomial divided by a polynomial. To graph it, we find the zeros, which give us the x-intercepts. The x-intercepts occur when y equals 0, right? So we set this equal to 0, and the only way we're going to get 0 is if x minus 3 equals 0, which is when x equals 3, right? So we solve that, we get 0, x-intercept is at 3, 0. Zeros of the denominator are at x equals -5 and x equals -1. Okay, so we draw our x equals 3 line, our x equals -1 line, and label it our x equals -5 line. Then we figure out the y-intercept. We just let x equals 0 and we get -3/5. And that's going to be like this line here. So the y-intercept is like right here. This is an x-intercept. These lines don't give us x-intercepts. These lines gives us vertical asymptotes, where the graph acts like reciprocal function coming down from here, coming up from here, and so forth. So we construct the graph. We figure out what the limit is as x approaches infinity, and we find that it's 0. Okay, so we construct the whole graph. Then, and this is the main thing I want to show you because we constructed fairly soon. Okay, same function. We set y equal to 4. And we solve this equation. Now, what's the first thing you do when you see this equation? You multiply both sides by the denominator. Remember me telling you, when you have denominators in the equation, you multiply both sides by the denominator, right? Okay, so we do that. And, here's the denominator, here's the denominator. We can rearrange this fraction as denominator over denominator times x minus 3 over 1. And this is just 1. So we end up with just x minus 3. So basically, this divides into this one time, leaving us x minus 3. Of course, now we got to write the x minus 5 times x plus 1 on this side. And then we have this. Now we put parentheses around x minus 5 and x plus 1 and use the distributive law to multiply that. So we have x is going to multiply the whole x plus 1. 5 multiplies the x plus 1. And we still have the 4, and this is still x minus 3. Then the x multiplies the x. There's x times x. X multiplies 1. There's x times 1. 5 multiplies x. There's 5 times x. 5 multiplies 1. There's 5 times 1. A step that, unless you're well practiced with the distributive law, you do not want to skip. But everybody skips it. Okay? Some people get away with skipping it. Don't assume you can. Write that step out. It doesn't take that long. Then x times x gives us x squared. X times 1 gives us x. 5 times x gives us 5x. 5 times 1 gives us 5. All that then is multiplied by 4. And x minus 3 is just sitting over here doing nothing because there's nothing to do with it yet. Okay? We're going to do something with that shortly. And I know the suspense is killing you. You can hardly wait to see what I'm going to do with that. But hang on for a minute. Be patient. We multiply all this by 4. So we get what? 4 times x squared gives us 4x squared. 4 times 6x gives us 24x. 4 times 5 gives us 20. It's a straightforward step. Then I rewrite the whole thing up here. And I take a good look at it and say, aha, that's a quadratic equation, which is now becoming relevant to your quiz. I mean, your test coming up. It's quadratic. We put that into general form and use the quadratic formula. Okay? So how do we put it in general form? Well, general form is ax squared plus bx plus c equals 0. Now, I'm not writing all that out because we've done enough quadratic equation. You should know that, okay? And know how to use it. So we've got the same equation written here. I'm going to go ahead and do the minus the quantity x minus 3 and minus the quantity x minus 3 because that's going to give us 0 on this side. When I write this side out, I don't try to do minus x minus 3 and line it up with all this stuff. I just write it as this minus x minus 3. Then I distribute the minus sign through, get negative x plus 3. And then 24x minus x gives me 23x. 20 plus 3 gives me 23. And there's my quadratic equation in general form. Okay? Very simple. What I've done here is actually quite simple. There are a lot of steps, a lot of ways to mess up. Okay? And I keep finding ways to mess up. I did one bonehead thing last time. I'll show you. I will go ahead and just solve the quadratic equation. I did some estimates here. I did some arithmetic that I think is kind of close, but it could be off by 10 in some of these, but it doesn't matter much. I get negative 4.5 or negative 1.5. Okay? Those are my solutions, and that's the kind of solution you might get. Now, that's approximate. And I said it was approximately equal, but I wrote it as an equal. No, I didn't. I have a little wiggly up here, but I'll make it a little bigger and wigglier. Okay. So that's pretty neat. That means that the graph I constructed where y equals 4 should intersect the graph at points where x is negative 4.5 and negative 1.5, right? And that's a big point I've got to make. I'm trying to make. So what do? I was visualizing the graph and said, yeah, that might work out fairly well. Well, I've already got the line y equals negative 3/5. One would be about this big. 1, 2, 3, 4 is up about here. There's y equals 4. It intersects the graph here and here. Now, this is a line x equals negative 5, and there's one estimate of x. Here's a line x equals negative 1. There's another estimate of x. So I'm estimating the x coordinate at this point and this point. Well, from negative 1 to negative 5 is 4 units. I can divide that in half. That would be negative 3. Divide from here to here in half. That would be negative 4. And it looks like this point is right at halfway between negative 4 and negative 5. So that sure looks a whole lot like negative 4.5, which is one of my solutions. And this one looks, if I was to make an honest estimate, this graph got kind of, I'd maybe estimate negative 1.4. It's about negative 1.5, okay? That's a full circle. We graph something, we get an equation, we solve the equation, we see if that's consistent with the graph. We get a reliable solution. We kind of check our solution. Everything comes around full circle. Now, the negative 4.5 and negative 1.5 are just estimates that I made. Those could be off by 1/10, maybe even 2/10. I don't think they're off by 2/10, but they might be off by 1/10. So, in these estimates, you know, they could easily be off by 1/10 in the other direction. All right. Speaking of mistakes that I shouldn't be making, and I do. Last time, if you remember, I got a polynomial that was supposed to be divisible by something, and it wasn't. Okay? And how did I get that polynomial? Well, first of all, I multiplied out, it is y equals x minus 2 times x plus 5 quantity squared. Okay? Well, I'm using the distributive law. I knew where I messed up. I did something really ignorant. Yeah, there it is. Okay. So I do my x plus 5 times x plus 5, x times the quantity x plus 5, 5 times the quantity x plus 5. I work that out. I write out every term and then put it together. I get x squared plus 10x plus 25. Now I multiply that by x minus 2, right? So how do I do that? I take x and I multiply by this. There it is, x times x squared plus 10x plus 25. That's x times this. Then minus 2 times that, right? So I did minus 2. No, I did plus 5. Okay? That's why the thing didn't work out. There are a lot of 5s running around, and my eye catches a 5. There are a bunch of 5s up here and 5s here. My eye catches those 5s, and just like AI, I hallucinate a 5. Okay? So this was a hallucination. AI can't help hallucinate. If I'm really careful, I can usually avoid it, but I wasn't very careful. So I'll just notice this is there's my hallucination for the week. Okay. That 5 should have been a 2, negative 2. Okay. Easy to make those mistakes. And I commented when I did this. This is not difficult. It's just hard to do it without making some kind of bonehead error. Okay. Without hallucinating something. There've been several times in the last week when I've seen a lot of 5s or seen a lot of something and written it down where it shouldn't be. So that's why it's good to check things and double check. And I'm going to give you a long division. See how you do with it. I think that should work. So that should be plus. So go ahead and work that out. And I'm going to clean a couple of boards and I'll come around and see how you're doing. Okay, well, this one turns out to work in just 2 steps. Okay, if you put a plus there. Okay, if you put a minus there, it takes a little longer. But I designed it so it would work out. So x goes into x cubed, gives you x squared times x gives you x cubed, and x squared times 3 gives you 3x squared. And it's plus Just have the plus on the 3. So when you subtract these, you end up with 0. So you bring down the 5x. And x goes into 5x 5 times. 5 times x plus 3. Go ahead and bring down the 5x plus 15 because you need 2 terms. 5x plus 15 subtracts off, and you're done. Okay? Now, it doesn't usually work out that nicely. Somebody did. Now I'll just do this quickly because everybody seems to know what they're doing with this. We got x squared, we get x cubed plus 3x. Of course, we got to put our minuses on. I should have done that up there. Little minus to remind ourselves. And we get negative 6x squared, that's 6x squared, plus 5x. X goes into negative 6x squared, negative 6x times. Multiply that back, you get negative 6x squared minus 18x. This is going to be a plus when you multiply it. So is this. It's going to give you 33x plus 15. X goes into 33x 33 times. 33 times x gives us 33x plus 99. Okay, well, we put our minuses on here, and 15 minus 99 is 84. So the remainder is 84. And we could write that then as plus 84 over x plus 3. Well, this acts like the quadratic expression x squared minus 6x plus 33. Okay? That would have a graph. It would have axis of symmetry at negative 6 or negative 3. It would have a vertex. If you put negative 3 in for x, what do you get? You get 9 and 18 is 27 minus plus 33 is 50. Okay? So you're going to have a 0 at it's not negative 3. The vertex is at x equals 3, negative b over 2a. So again, you get 9 minus 6, which is 3, plus 33, which is 36. This polynomial would have a graph with a vertex at x equals 3, y equals 36. We have a y-intercept of 33, which doesn't make sense. Hang on a minute. 3, it's negative 18. Okay, I messed up my calculation. I did 9 minus 3. It's 9 minus 18. So it's not y equals 36. It's y equals 24. And then the y-intercept, if x is 0, y is 33. There's y-intercept. And we know that we have a point symmetric with this on the other side of the axis. So right there's our graph. And we can also say that this is y equals x minus 3 squared plus 24. If you square the x minus 3, and add what you get, you're going to get x squared minus 6x plus 33. The vertex form, that's general form. So this is a graph of this part of the quotient. Now, if you add 84 over x plus 3, that's going to change the y values. But as x gets really big, it's not going to change it by much. So if you zoom out on this graph, it's going to look a lot like the graph that you would get if you extended this quadratic. That's all relevant. I said it kind of quick because it's kind of review stuff we've already talked about. I think I recorded everything I did over here. Want to find the zeros of this function. There's a theorem in your book that tells you basically that the zeros have to be between -5 and 5. It can't be any further. I could explain why that's so, at least for something with linear factors. As quadratic factors, the explanation's a little more involved. You're not required to know that. You're not going to be tested on it, although if you use it on a test, it might give you an extra point. All you do is you look at the biggest number here and ignore the minus signs. Okay, so it's like you could say, okay, here's -4, and here's 4. You go 1 to the left of that and 1 to the right of that. So here's -5 and 5. All your zeros have to be between here and here. Again, you don't have to know that. All I'm going to say is we're going to try. We're just going to try these numbers to see if we can find a zero. If you're really fanatical about it and thought you might be going to find one, you could go as far as -5 and 5. But just for simplicity, we're going to try these. You can pick any of those numbers you want. I would start with like -1 and 1 because it's really easy to do the calculations with 1. The bigger the number, the more the calculation. So plug whichever number you want to into this and see if you can hit a 0. Okay? Plug one of these numbers in and see if this gives you 0. If it doesn't, try another one. Okay, everybody did well. Only a couple of people used the obvious, easiest choice. It's always easy to plug in 1. Okay, so I gave you all these choices. If you use a little sense, you see that every power of 1 is going to be 1, right? So you're going to just get 1 plus 2 minus 4 plus 1, which is 0. Okay, so Okay, easiest number to try is x equals 1. Let's see if we luck out. Now, I would write this out. I'd say f of 1 equals, just so when I come around and look what you're doing, I know what number you're using. And so you know what number you use, okay? So that's a really handy, easy way to use function notation to show yourself what you're doing. It only takes about half a second to write that out. And now you're going to have 1 cubed plus 2 times 1 squared minus 4 times 1 plus 1, which equals 1 plus 2 minus 4 plus 1, which equals 0. Aha. Okay. If you try any of the other numbers, it won't give you 0. I don't think. Could. Not impossible, but I'd say less than 1 in 100 chance. Without thinking anything more through. Let's see what the other zeros are. We've got 1 0. We can find the rest of the zeros. All we have to do is say that our function equals x minus 1 times a second degree polynomial. It's a polynomial. If 1 is a 0, that's because x minus 1 is a factor. Okay? Because we know if we see the factors, we can easily find the zeros, right? If we don't see the factors, we got to find them. And sometimes you got to have a little luck. And sometimes you're never going to find it. Doesn't mean that there isn't a 0. It just means there's no way to find it exactly. Okay? And that actually happens the majority of the time in the real world. Okay, so anyhow, we have this. Well, if this equals this times this, then what does this equal? This has to equal this divided by this, right? Now, we divide both sides by x minus 1, we're going to get this over x minus 1, right? That's going to equal our second degree polynomial. That's simple algebra. Again, this equals this times this, so this equals this divided by this. Just divide both sides by x minus 1. It's a straightforward rearrangement. How do we divide this by x minus 1? Log division. So this exercise, let's divide x minus 1 into x cubed plus 2x squared minus 4x plus 1. Now, since x minus 1 is a factor, this has to come out without a remainder. Otherwise, this wouldn't be a factor. So see what you get. Okay, people are doing correct steps, but they're making little clerical errors, acting too much like me, okay? A few little hallucinations there, but I think everybody's okay. So let's be sure. X goes into x cubed, x squared times. That gives us x cubed minus x squared. Now, some people wanting to put a minus down here with parentheses around it. That's fine, but a minus with the parentheses around it doesn't directly tell you that this minus x squared has to be subtracted, so you're going to have to add x squared. Okay? And you're going to have to subtract this. Now, what you get is x cubed minus x squared. So you don't replace this minus with a plus, and you don't put a big minus in front of this. You just put a little plus sign here and a little minus sign here to remind yourself that you're subtracting these, so whatever their signs are, change the sign and then add. Okay? So I add x cubed to negative x cubed, and I get 0, so that goes away. I add x squared to 2x squared, and I get 3x squared. Then I'll bring down that negative 4x. Okay, well, x goes into 3x squared 3 times. That gives us 3x squared plus 3x. No, it's minus 3x, sorry. Again, my picks up a minus sign there, and I want to hallucinate with it. Okay. So I write my little plus there to remind myself that since I'm subtracting the negative 3x, I've really got to add 3x to the negative 4x, and that gives me negative x. And I bring down the plus 1. And x goes into negative x. That should have been a 3x there. I didn't write the x. X goes into negative x, negative 1 time. And we get negative x plus 1. Okay? And that does. Fair enough? Okay, well, where does that leave us? Let's see what I can get away with the boards here. Bring this over as far as I can without losing it. And put this one over here. Hope it balances. Okay. So what have I concluded? Just to summarize, f of x is x cubed plus 2x squared minus 4x plus 1. F of 1 equals 0. So x minus 1 is a factor. Get another factor. We do x minus 1 divided into x cubed plus 2x squared minus 4x plus 1. And we get x squared plus 3x minus 1. So f of x equals this under the square roots. I've got a glitch on the board there. I've got to fix that. Okay, again, here's our f of x function. What happened on there? Okay, there we go. Here's our f of x function. And if I divide this into that function, I get this, meaning that this equals this times this. So f of x is x minus 1 times x squared plus 3x minus 1. Okay. Now, can we find a 0 of x squared plus 3x minus 1? Well, actually, there's a way we can always find a 0 if it exists. This is just a quadratic function. y equals this. And if we want to find a zero, that's where y equals 0. So we get this equation here, which gives us x minus 1 equals 0, or x squared plus 3x minus 1 equals 0. Well, this one has solution x equals 1. You can try to factor this if you're good with factoring, and a lot of people are, but it's not going to work. We got to use a quadratic formula. Okay, that's easy. I mean, it's a little tedious. If you're like me, you make a mistake about every third time. But we get x equals -3 plus or minus the square root of 3 squared minus 4 times 1 times -1, all divided by 2 times 1. And that's -3 over 2 plus or minus the square root of, that's going to be 9, and that's going to be part of the square root of 13 over 2. Okay. And that's going to be approximately equal to -3/2 plus or minus square root of 13 is about 4.7. And that was there, 3.7. Yeah, 13 is between 9 and 16. It's somewhat closer to 16, so that the square root is somewhere between 3 and 4, somewhat closer to 4. So I think 3.7 is probably to the nearest tenth. Could be 3.8. I don't think it's 3.6, maybe. Okay. So what's that equal? Well, this is like, I'll go to decimals at this point because we don't have nice fractions. We don't have a nice fraction here with integers, okay? We're down to decimals. This is then plus or minus 1.85, which gives us -3.35 or 0.5. So x is 1 or -3.35 or 0.35. So now f of x is approximately, because the square root of 13 is an irrational number. You can take it out to 10,000 decimal places and you're only getting started, okay? Got to round it off somewhere. So I rounded it off to what I could more or less trust in my head. You've got a calculator. You do a few more decimal places if there's a good reason to do it. But as far as figuring out what the graph looks like, 3.35 and 0.35 are plenty close enough for a hand sketch graph, okay? So f of x is approximately x minus 1 times x minus 0.35 times x plus 3.35. That's what this is approximately. If you multiply all that out, if you expand that, you are going to get something close to 1 here. You're going to get something close to -4 and something close to 2 for your factors, okay? The graph we've already figured what the zeros are. They're at x equals 1, x equals 0.35, and x equals negative 3.35. What's the y-intercept? Well, you plug in x equals 0, you're going to get negative 1 times negative 0.35 times 3.35, which is pretty close to 1. And of course, if you use the actual function, you do get 1. So that we know from the original function the y-intercept goes here. You have a 0 here, a 0 here, and a 0 here. Now you're zoomed out. We have the cubic function because that's your leading term. When x gets really big, x cubed is way, way bigger than any of the other stuff. So it acts like y equals x cubed when x gets big. So zoomed out, it looks like this. As I've said before, then we got wiggles. We got to wiggle around here in order to go through all these zeros and all these intercepts, all the x-intercepts and the y-intercepts, which is x equals 1. So it's like we got this little region here. I'll circle this to show that that's our little blue region that we magnify to get this big region, this big picture, which is where all the interesting stuff happens. Y equals x cubed is kind of boring. It's where the wiggles and stuff are that it gets interesting. And in that area, we know that it's got to come up from, if we go to the left, it's going to approach negative infinity. If we go to the left at this point, it's got to approach negative infinity. It's going to do this. Then it's going to come up here, down through here, and back up through here, because here's our long run. Just like this is our long run. And this is our long run, because this is our long run. I'm writing that really small, but you know what I wrote. Okay? Do we understand this? Again, for big X, only the x cubed makes much difference. For small x, all this other stuff makes the thing wiggle around. Okay? So there's what the graph looks like, understanding that by this point, we're well on our way to being close to the x cubed graph. Now, what we did this time was we figured out that 1 is a 0 just by trial and error. There are other tricks we can use to make more accurate estimates, get more accurate versions or more accurate numbers to try for x equals 1. And the text will show you some of those. So I'm not going to explain them. I think they're easy enough to understand if you look at the examples. And I want to explain something that's less easy to understand. It'll be due also by Tuesday. I got the right numbers. Okay, we reduced that last thing to this form, okay? This is a linear factor. This is a quadratic factor. First place, any polynomial is a product, can be reduced to a product of linear and quadratic factors. Now, those factors might involve irrational numbers, so you can never do it exactly. But the theory is, it's a theory, I first learned to prove that theorem in a senior level abstract algebra course for math majors, okay? Fairly advanced course. And the theorem uses a lot of abstract mathematics, stuff way beyond anything. So unless you really want me to, I'm not going to prove that. But you can prove that any polynomial can be reduced to linear factors and quadratic factors. Okay? Now, in the case of this one, this quadratic factor actually factored. Which one was negative? Yeah. I just don't trust my memory. I'm hallucinating too much lately. And I haven't even been using a lot of AI. I just do it on my own. And then x plus 3.35. These are all linear factors. Okay. Because a quadratic factor had zeros, that could be reduced by finding the zeros. We reduce this approximately to this. Now, there are exact numbers that could go here, and the exact numbers involve the square root of 13. Okay. These are the exact numbers, -3 halves plus square root of 13 over 2, -3 halves minus square root of 13 over 2. Those are the exact factors. And I could have written them down like that. Okay, well, it doesn't always happen that the quadratic factors you can get when you reduce these things are reducible. If it had been, just checking the time, make sure how fast I got to talk. I don't want to have to talk too fast. It's just kind of big deal. Not all that hard to understand, but it's a kind of really neat thing to understand. Okay. Let's consider this. Okay, x plus 2 is a linear factor. X squared plus 2x plus 6 is a quadratic factor. Maybe it can be reduced. In fact, x squared plus 2x plus 6 equals 0 for real numbers. Now, the example we saw earlier, we saw that this thing could be reduced because these are real numbers. Okay, they're about negative 3.35 and 0.35. So we could write the thing like this. In this case, I'll say, let's see. X squared plus 2x plus 6 equals 0 if and only if x equals negative 2 plus or minus the square root of 2 squared minus 4 times 2, times 6, all over 2 times 1. That looks okay, doesn't it? Well, what happens though is 2 squared is 4. 4 times 6 is 24. So that's 4 minus 24. We get negative 20 under the radical. And that negative 20 is a problem because there's no real number that we can square and get negative 20. You square any positive number, you're going to get a positive. If you square any negative number, you're going to get a positive. You can't get negative 20 by squaring a real number. So we say that's okay, that's minus 2 plus or minus the square root of 20 times the square root of negative 1, all that divided by 2. Now, negative 20 is 20 times negative 1, so we can say the square root of negative 20 is the square root of 20 times the square root of negative 1. But what's the square root of negative 1? It's not a real number either. But we're going to call that our basic imaginary number. Well, I tried to make a good I there. That's I for imaginary. And the camera seems to be cutting off the bottom of the screen. Yeah, do something about that. And it's camera. Be able to look at the video and see if the camera just kind of migrating on me. I don't think so. I mean, everything's pretty firm. Don't see any reason why we'd be doing that. Okay, and I am still not sure I got it. Sorry. Okay, the floor. Okay, I just barely have it. Doesn't make sense. Okay. Well, this number can be written -2/2 plus or minus the square root of 20/2, and that can be simplified. But this says our conclusion is this is irreducible. Okay. So if you factor any quadratic, it'll factor down into some linear factors and some quadratic factors. If the quadratic factor is like this, it can be reduced and we end up with linear factors. Okay. If it's like this, where this thing can't be equal to 0 for any real number, that means there's no x-intercept. X-intercept has to be a real number, right? There's no x-intercept. So this is not going to attribute any x-intercepts to a graph. All right. Now there's even more. There's the arithmetic of complex numbers, which is really pretty easy. And I'm going to kind of leave that to open math. And if we need to talk about it more, we'll do that next time. Okay. Now the test is in the testing center. You didn't have it done by Tuesday. Did you get an email about the testing center being closed at some time? Everybody should have gotten an email. I'm going to double check that email because it might be like tomorrow and Saturday, and people might be planning to take the test tomorrow or Saturday. Most people are probably going to take it at the last minute next Tuesday. So that might not affect too many people, but it certainly might affect some. So I'm going to double check that. I meant to double check that earlier. And I'm not absolutely sure it's this weekend. It's a very bad weekend to do that on. They're replacing doors in the LRC building. And there's going to be a lot of noise and dust, so they're closing the building 2 days, on a Friday and a Saturday. Check your email. But I will send out an email to everybody if it's this weekend, just to be sure everybody's informed. Okay. Okay. Very good. Good luck on the test. And let me know if you have questions.